Hello, and welcome back to the course on classical electromagnetism. So we are still on the fourth chapter of this course. So in the previous lessons, we have discussed about the force on moving charges. So if you have a moving charge Q with velocity V, that is the force on that moving charge exerted by the external magnetic field. And if you have current carrying conductors, then the force on them will depend on the distribution of the current. If it's just a line current distribution, you will have I cross V dl. And if you have surface currents or volume currents, you have these other equations. So the current is related to the linear charge density. The surface current is related to the surface charge density. And the volume current is related to the volume charge density rho. So for this lesson, we will be focusing on how to solve for the magnetic field of a current element or a current distribution. And the main law that we will be using is the law of Biot-Savart or the Biot-Savart law. So you actually have been exposed, or this has actually been introduced to you in your basic electromagnetism. So this is actually analogous to Coulomb's law in electrostatics, and this is the main equation in solving the magnetic field of current elements or a current distribution. So it's an integral equation, mu naught over 4 pi I cross r dl over r cubed, where this r here is the separation distance vector. So the separation distance between the source, the current element, or the distribution, and the point where you want to find the magnetic field. So r here is the position of the point where you want to find the magnetic field. Usually we call that the field point. The prime coordinates here just refers to the source. So you can rearrange this. Instead of using I as the vector, you can have dl as the vector. So actually I think this is the more familiar form for you. So I dl cross r hat over r squared. Again, r here is the separation distance between the source point and the field point. Of course, if you have IDL here can be replaced by KDA or JDV if you have surface current distribution or volume current distribution. So in a similar manner with the electrostatics, we will try to analyze this using the source and the field components. So if this is your current element and you want to find the magnetic field at point P, then the current element is the source, point P is the field point, and you just need to take the position of the current elements, r prime, source point, and the position of the field point, which is r, and take the separation distance, the r vector, the curly r vector. So this is just r minus r prime. So the curly r vector is r minus r prime. And the magnitude here, the r hat vector here, the unit vector r hat, is just the separation distance vector over its magnitude. Okay, so similar analogy with electrostatics when we discuss about Coulomb's law. So as you can see, the basic source of magnetic field is actually the current or a moving charge. So a moving charge or current creates its own magnetic field aside from its electric field. And the joint fields is called an electromagnetic field. So here we will just be focusing on the magnetic field. So first example. So find the magnetic field a perpendicular distance s from an infinitely long straight wire carrying a current I. Okay. So here we will assume that the axis of our current or wire is the z-axis. So we will place our origin somewhere at the center of the wire. So this is basically our R, the location of the source point. So our source point is here. And if we get some differential element, our current element, say here, this will be our current element, DL. And its position is this one. This is R prime. So therefore, the separation distance, the distance from the current element to our source point, will be this one. So this will be our separation distance vector. Okay, so from here, our R is clearly has a distance. This one, our R is S, and this direction is in cylindrical coordinates. That direction, the radial outward direction, is S hat. Our R prime is clearly along the Z axis. So assuming this distance is Z, this direction is Z hat. So we are using cylindrical coordinates here. So therefore, the separation distance vector is R minus R prime. This will become S hat minus Z hat. And if we take the R hat, the unit vector, so it's just this vector divided by its magnitude. So the magnitude is just the length of this vectors, the separation distance vector. And since this is Z and this is S, so this is a right triangle, so you have Z squared plus S squared. So it's just a square, the vector, the curly vector R, S hat minus Z hat over its magnitude, which is the square root of S squared plus Z squared. Okay. So let's now try to find the magnetic field. So we will use the law of Biot and Savart. So this equation. So I'm now gonna erase this one, this part here. And I'm gonna go to my board mode. But I will have a lot of space. So this is our R hat now. And we will start with this equation. Okay. So DL, our DL here is clearly DZ along the Z axis or the Z direction. So if you will, I'm gonna go back. So my DL here is along the Z axis, so it's DZ Z hat. So starting with this equation, my magnetic field will be mu naught over 4 pi integral of I. My DL will be DZ. This direction is Z hat. Cross with R hat, which is this one. So you will have S hat minus Z hat over square root of S squared plus Z squared. And then in the formula divided by R squared. So divided by R squared. So R squared, this one is just the square of this. So you have S squared plus Z squared. So this is what happens when we substitute all the values to our equation. Okay. So you will notice there's a cross product here. Z cross S, the answer is actually phi hat. Z hat cross S hat is phi hat. But Z hat cross Z hat is 0. So you cannot, the cross product of a vector itself is 0. So there will only be one term. Walay contribution, there will be no contribution for the second term. There will be only one term, Z hat cross S hat. The Z hat cross Z hat will have 0 contribution. Okay. So you will have mu naught I over 4 pi integral of s dz over s squared plus z squared 3 halves, and the direction is p hat. So that is the finalization. Okay. So we use trigonometric substitution. So we have actually a triangle here, a right triangle. So this side of the triangle is z, this side of the triangle is x, this is our r, this is our r prime, and we can let this angle as the angle theta. So using trigonometric substitution, we let the tangent of theta is opposite over the adjacent, so z over s. So we can let z is equal to s tangent theta. So of course, the derivative of that is secant squared. The derivative of tangent is secant squared. And later, we will use this identity 1 plus tangent squared, or tangent squared plus 1 is just secant squared. So using this trigonometric substitution, I will let that as a little exercise for you. You will arrive at this one. Cosine theta d theta. This whole term here, using trigonometric substitution, will just become cosine theta d theta, where theta is, if we go back, so this is my theta here, and the theta actually corresponds to the location of the differential elements. So the differential elements are from the this is an infinitely long, so from z is equal to negative infinity to z is equal to positive infinity, and that value of theta is that value 180 degrees to negative 180 degrees to negative 90 degrees to positive 90 degrees. So theta is measured from this axis, no? That is our theta, like that. So you will now measure theta from negative 90 to positive 90 degrees. So negative pi over 2 to pi over. So the theta here, this theta angle here is from here, negative 90 degrees to positive 90 degrees. This is the 0 degrees theta. Okay. So in doing so, we can solve for our magnetic field at r. Our r now is in cylindrical coordinate is s and phi. It has no z dependence, so you will actually get this one, 2 pi s phi hat. So it only depends on s for the magnitude and phi for the direction. So it's a summary. So this is our result, and this is actually the result that you use in your basic electromagnetism. This is the field near a long straight current carrying conductor, unit I over 2 pi s. So, but maybe in your basic electromagnetism you use r instead of s. But here we will be strictly using the cylindrical coordinate for the cylindrical coordinates. So this is what this means. So if the current is the direction of your thumb, then the magnetic field actually curls around your current element. So that one. So you will notice that at the top of the wire, the magnetic field is pointing out of the page. The magnetic here is actually out of the page. So this one, the symbol is a dot, but below the line, the magnetic field is actually into the, or below the wire, the magnetic field is into the page. It will curl around, so goes out and goes inside here. So it curls around. So that direction, the curling direction is the phi direction, the phi hat direction. Okay. Moving on to another example. So find the force between two parallel wires separated by a distance d. So actually, this have already been introduced before in your basic electromagnetism. So from the previous example, we know that a current carrying wire has its own magnetic field and it's actually curling around. So meaning, and in the previous lesson, a current carrying conductor will experience a force due to an external magnetic field. So since these two wires have their own magnetic fields, they will actually exert a force on each other. And actually, the force is how do we call this? Uh, Mutual. The force is actually mutual. So I1 will exert a force on I2, and I2 will also exert a force on I1. So it's actually the negative of each other. So the force exerted by I1 on I2 will be the negative of the force exerted by I2 or I2 on I1. So by virtue of Newton's third law of motion, so the law of action and reaction. Okay. So let's just consider solving the force exerted by I1 on I2. Now, we already know that B1 a function of S1. It's a function of S1. S1 P1. From our previous result, we know that a current carrying wire, say carrying a current of I1, will have a magnetic field, mu naught I over 2 pi S. So there's a subscript 1 here, indicating that this is the magnetic field of I1. Now, at the location of 2, or I2, assuming this will be our axis, so assuming this is our axis, this is the positive X, this is the positive Y, and this is the positive Z is going out of the page. So the magnetic field due to I1 at the location of 2, so it will curl around I1. So at the location of 2, the direction of magnetic field is actually the direction of B1 is actually into the page. So at the location of wire number 2, the direction of the magnetic field of B1 is actually into the page, because it's in the lower part of with respect to I1. So this is I1. The magnetic field of I1 is my fingers. So at the location of I2, it's into the page. So that direction actually is, with respect to the Cartesian, it's the negative z-axis. So at the location of wire number 2, ang B1, so S1 is the distance from wire 1 to wire 2, the location of wire 2. So S1 here is just equal to D. So at S1 is equal to D, so its magnetic field is actually mu naught I1 over 2 pi. S1 is equal to D, and that direction is actually negative Z hat. So this is the magnetic field of B1 at the location of I2. And this is the magnetic field that we will use in solving the force exerted by I1 on I2. So the force exerted by 1 on 2 will now be I2, and then you will have DL2 cross B1 at point D. So IL cross B. So every differential element DL2 in your wire number 2 will experience a differential force. And if you integrate all of that, you will get the total force experienced by all the differential current elements, or the differential length elements. So in our case, DL2 here is along the positive X direction. So it has the same direction as the current. So DL2 here will be dx, and its direction is x hat. Okay, so you try to cross this one, dx x hat, and b1, which is mu naught I over 2 pi d negative z hat. So x cross z is negative y. There's a negative sign, so the value or the direction. So from here, by crossing the directions, you will already get the direction of the force F12. So dl2, which is x hat, you cross it with v1, which is negative z hat. The answer of that is y hat. So therefore, F12 is actually in this direction. The force exerted by wire 1 on wire 2 is towards itself. So it's an attractive force. So in doing so, you will actually get, I'm just going to show you the answer. I'll leave the simple integration to you. You have unit I1, I2 over 2 pi d integral of dx. The direction is y hat. And this integral of dx, this is just the total length. The total length of the wire. So that's the total force exerted by I1 and I2. And similarly, for the force exerted by I2 on I1, F21, it will have the same magnitude, but the direction will be opposite in the negative y axis. So it's a mutual force. So the law of action and reaction. So instead of using the force, we can actually get the dF over dL, the force per unit length between two parallel current carrying wires, and the magnitude is this one. It only depends on the magnitude of the two currents, I1 and I2, and their separation distance, d. So it's actually in this equation that the definition of 1 ampere was formed. So for the last example, we have a circular current loop with radius r, and find the magnetic field at the axis, so along its axis. So here we will assume that its axis is the z axis. So I redraw the loop. So its axis is the z axis. So meaning, for every differential element here, dl, it will have a contribution differential magnetic field. So the differential length is our source. This is our origin. So this is our r prime, and this is our field point. This is our r. So our r here is clearly z hat. It has a direct a magnitude of z and direction of z hat. Our r prime here, this one, has a fixed magnitude r, the radius of the loop, and its direction is s hat. So that is the s hat direction. So therefore, our separation distance vector, the curly r vector, this vector, is just r minus r prime, and you will get z prime minus r s prime. And since the magnitude of this is, by Pythagorean theorem, this is just the hypotenuse. This is just c squared plus s squared, or r squared rather. So the r hat vector, the unit separation distance vector, is given by this vector here. Okay, now from the law of Biot-Savart, the magnetic field actually depends on this term here, dl cross r hat. The direction of the magnetic field is actually the direction of this cross product, dl cross r hat. Now, if you take the dl cross r hat in our scenario, our dl is in this direction, in the phi direction. So using right hand rule, dl, for this specific dl, so dl cross r hat, and you will get db in this direction. So that's the differential magnetic field due to this differential current element. Now, since our r hat has two components, z and s, for every dl here, there is actually a DL on the other side, wherein if you take the DL cross R hat, its direction will be in the opposite direction. It will be the dB. Now, these two differential magnetic fields, due to these two opposite DLs, will actually, or the S components of these two magnetic fields here will actually cancel out due to symmetry. Only the Z component will remain. So this is the X component. Sorry, not the X, the S. This is the X component of this first magnetic field, and this is the X component of this other magnetic field. And these two S components, dBs component, dBs component, will actually cancel each other out, and only the Z component will remain. So therefore, in our calculation, only the Z component will actually have a contribution. So only this, the Z hat component of R hat, will actually have a contribution. So from the equation of law of Biot-Savart, from this equation, so we will only take the Z. We'll only take the. No, I'm sorry. Not this component, but the Z component of the L cross R. Sorry. So we'll still use this R hat, but only the DL cross R hat, the Z component, will contribute. We'll only need to use this here. Only the Z component of this DL cross R, of this cross product, will actually have a contribution. Okay. So let's solve for DL cross R hat. So DL, if you will notice, DL is from this equation, this is our DL. And you will notice that the total length is the circumference of the circle. So that's actually, DL is actually R d theta, where theta is from 0 to 2 pi. So you will get 2 pi r if you want to solve the total length. So R d theta, and its direction is phi hat. So if you cross that with this one, so you will have DL cross R hat. What do you get? So you have R d theta phi hat. You cross it with, so I'm just gonna go to my board work, so I have a lot of space. You cross it with this, the R hat, which is Z hat minus RS hat over the square root of Z squared plus R squared. And you will get what? You will actually get two terms. So you have phi cross Z, the answer of that is S hat, and phi cross S hat, the answer of that is negative Z hat. But there's a negative sign here, so you will have a positive Z. So you will have RZ d phi this is phi. So RZ d phi over separation, this the magnitude, so this is the magnitude R. Square root of Z squared, since we expanded this. This is the S hat plus R squared d phi over square root of Z squared plus R squared Z hat. Okay, so the DL cross R hat has two components, the S hat component and the Z hat component, and only this component will remain. So this DL cross R hat na Z component will contribute to the magnetic field. But again, the S components will actually cancel each other out. So because you can justify that by saying due to symmetry, the S components of DL cross R will cancel each other out, so that you can only use you are allowed to only use the Z component. So the Z component. So your formula will look something like this. It's that one. So we'll start. You will start with that this formula here. So substituting all of that, so your magnetic field now will be equal to mu naught over 4 pi I, and then the z component of dl cross r is this one. So r squared d theta, r squared, sorry, d phi over square root of z squared plus r squared z hat. So that's the z component of dl cross r hat over r squared. So r squared is just this one. So I'm just gonna lump them to 1, z squared plus r squared to the 3 halves. So you have square root plus z squared plus r squared, then you have 1 plus 1 half over 3 halves. Okay, so you will notice this, there's only one differential element, d phi, and d phi is evaluated from 0 to 2 pi. So you will get the magnetic field only depends actually on z. Only one cylindrical coordinate here, it's z. It's mu naught I r squared over 2 z squared plus r squared to the 3 halves, and the direction is z. So this is the magnetic field at the axis of a circular current loop. So as a summary, so this is the field at the axis of a current loop, and at the center of the current loop, that is at z is equal to 0. So at z is equal to 0, you will get this result. So actually, you have been always using this result in your basic electromagnetism. So it follows the right hand rule. Direction of magnetic field of a current loop follows the right hand rule. So if the direction of the current are my fingers, then the direction of the thumb is your magnetic field. So the right hand rule, so like that. So actually, in reality, the magnetic field along the axis of the direction is actually uniform, but on the other side, so at the center of the loop, the direction of the magnetic field is in that direction, but on the side of the loop, it will actually start to bend like that. And then in this part of the loop, it will actually curl around the loop like that, and downwards it will still be like that. So if you're familiar, this is the magnetic field pattern of a magnet. So this is the north side, and this is the south. That is the north pole there, and that is the south pole. So essentially, a current loop is a magnet. In fact, in your basic electromagnetism, you have related this. You have an application for this, the electromagnet. You have many current loops, and basically you have an electromagnet, a magnet wherein you can control the strength of the magnetic field by just changing the size of the loop, the number of loops, and the current, the source of the current or the potential of which powers the current, or pushes the current from loop. Okay, so that's the end of this lesson. So far, we now have discussed how to calculate the magnetic force on current elements, and also I define the magnetic field of the current elements themselves. So in the next lesson, we will, in the same manner with electrostatics, we will be discussing the curl and the divergence of a magnetostatic field. So I will see you again in the next lesson.